Well, this is the first of two videos on the reactions and synthesis of conjugated dienes. Synthesis and reactions of conjugated dienes. Conjugated dienes are typically defined as two alkenes that are separated by a single bond, so an alternating or pattern of double and single bonds. But a more precise definition might be the case where we have a diene, two alkenes, that have no breaking in the overlap of p orbitals. So that looking at the p orbitals on each of these carbons, these four carbons, we could treat those hydrogens as in the plane that are on the ends, two of them on each end and one on the middle. And we could say that the p orbitals would be coming straight out towards us that are on these sp2 hybridized carbons within the diene, and there's no break between the p orbitals. That's a more fundamental definition of conjugation, is a unbroken yoking of p orbitals together. Conjugated, yoked together, meaning p orbitals, four of them in the diene, are overlapping. Things change when that happens, and we'll get into more of the electronic picture of dienes through MO theory, which we have to consider for Diels-Alder reactions. We'll start looking at, I guess, how two electrons here can actually be scattered amongst the four p orbitals. That's something that's very hard for students to see sometimes, is that we can see the bond line structure, and we can even think that these two electrons are located, these pi electrons, between these two carbons. But it's a little bit harder for students to jump to the idea that two electrons can be scattered amongst four p orbitals. We'll start to do that in the second video. The first video here is just looking at some radical chemistry to do allylic halogenation of an alkene, meaning next to the alkene. Allylic means next to the alkene. We can have halogenation, allylic halogenation. We'll wait on dehydrohalogenation, which is just looking at E2 chemistry, wherein we have a strong base, an Rx, and we can have from that Rx elimination chemistry, strong base, secondary Rx. We would propose E2 chemistry. We'll wait on that, but then we'll jump from allylic halogenation to electrophilic addition. Electrophilic addition reactions, wherein all we're going to do is consider how dienes would react with HX, HBr, HCl, strong acids. Somebody's going to have to come in and attack a proton. We're going to look at pi electrons coming and attacking the proton. So that's all we'll do with this video. In the second one, please hang on to your hats. Diels-Alder reactions require that we come back to this idea of two electrons amongst four atomic p orbitals. Well, let's cover just briefly how we draw a product for allylic halogenation. If we see chlorine or bromine and light, or sometimes you might see, instead of Cl2 and light, you might see as an alternative NBS and light, or heat. NBS is a N-bromosuccinimide. It's a way to halogenate at the allylic position without having a lot of the diatomic form of the reagents Br2 in solution. So this is an alternate way of getting halogenation using bromine, wherein we don't have a lot of Br2 present. Now, why would that be bad to have a lot of Br2 in the diatomic form? Why would that be bad? Well, because we could have an electrophilic addition of Cl2 or Br2. Electrophilic addition, and we don't want that. We want to create as much as possible Cl radicals by the interaction of light with this Cl2. Cl radicals dissociated, a homolytic cleaving, and have these Cl radicals dominate the reaction, not Cl2. So we want more of this and less of this. So we can do that with at least bromine by binding it into a molecule where it still has a slow release program of Br radicals out of NBS, and I'm not going to go into that detail as far as how that happens, but NBS is used as an alternative to Br2, and with light or heat we can initiate radical formation of Br radical, just like we can initiate here Cl radical formation. So as this reaction goes, we know that there's 3 steps to every radical reaction: initiation, propagation, and termination. So we can propose initiation with light. The chlorine radical can come and grab a hydrogen, half arrow I guess, and we can have the electron given back to that carbon that is next to a double bond. Why is that important? Because we have resonance, delocalization of a radical next to a pi bond. Not on a pi bond, but next to. So we can have half arrow, just to show the resonance form. We can see how these two are indeed resonance forms. So that gives us stability of a radical that we would not have if we did not have the pi bonds. So we tend to favor, these again are very, I guess, high energy intermediate, but we tend to favor, in the presence of radicals, we tend to favor propagation to the alkene such that the radical, by abstracting a hydrogen, is propagated to the carbon. So that's initiation, propagation, and now we can have termination. We can have that Cl radicals, those radicals that are floating around, terminate by binding these radical positions. Now there are of course other things that can happen in solution. We can have the radicals attacking radicals that are, these 2 of these floating around in solution. These are just resonance forms of one structure, but if 2 of these found each other, then we'd have a different type of termination. But we can have the concentration of these hopefully set that we can get enough termination reactions to give a significant amount of this product, wherein the carbon radical terminates with the chlorine radical. Here, that gives us this product. Radical to radical. I'm not showing those arrows, but radical combines with radical to give us this product. Or we can have the same structure where the lone electron, the radical, is expressed here. We can also get this product. And we get a mixture then of these two. How much of one relative to the other? Well, experimentation needs to be the final authority on that, but we could propose maybe this double bond is more stable by Zaytev's rule. But radical reactions are hard to control, so really just safe to say at this point we get a mixture. Now better control of these reactions are seen with Br2, just more stable radicals. These are a little more soft, you might say, and therefore more selective. I've said NBS is a source of Br2. If we have too much electrophilic addition across the double bond, competing reaction, we can use NBS as a source of Br2. So instead of Br2, we can see this written in, and then light or heat to initiate radical formation. And we're not really considering control to favor one of these 2 over the other. It's difficult to achieve that control. Okay, well, we've talked a little bit about allylic halogenation and why that was, I guess, a favored position. Just more on that. We can show again allylic radicals having 2 resonance forms, and we can show it not just with arrows, but how the p orbitals overlap. There are 2 p orbitals here that hold 2 electrons, the up and down arrows, and then 1 p orbital that holds 1 electron over here that's representing a radical. And we can have, again, 3 electrons, 1, 2, 3 amongst 3 p orbitals, and we're going to consider those to be resonance delocalized radicals. We can also do the same thing with anything next to a pi bond. We could call this a allylic carbocation, but because it's in a position where there's a benzene ring next to it, we give it a special name. Not allylic next to a pi bond, we call it benzylic. And it could be a radical here, an anion, a cation. We can have a stabilization by resonance of that positive, negative, or radical radical that we would have at the allylic position. We can again have a radical here, an anion here, or a positive charge here, and these resonance forms would still apply. We'd just change this from positive to negative or to a dot. So this allylic and benzylic stabilization is very important of cations, anions, and radicals. Now we've already talked a little bit about the picture of a diene. As we look at a diene that's conjugated, the key to that picture and the difference between a non-conjugated system and conjugated is the overlap of 4 p orbitals. So 1, 2, 3, 4. We can typically say if you have 3 or more p orbitals overlapping, you have a conjugated system. You have something more than just a pi bond if you have 3 or more. So 1, 2, 3, 4. So we could actually have said this is a conjugated radical, conjugated to the neighboring pi bond. We can have a conjugated diene, more than 3 atomic p orbitals, and these red dots representing the electrons. This would be a non-conjugated diene, where we have no communication of the pi bond here with the pi bond here. So looking at other examples of conjugated systems, we can have not just alternating double and single bonds, but really looking at p orbital overlap. We can have a p orbital here, of course p orbital here overlapping to give a pi bond, but we know that there's a pi bond here, and we could have these aligned, and they will be most typically aligned, so that the p orbitals overlap. So this would be our, if we were to circle, area where we have atomic p orbital overlap, 4 p orbitals overlapping. Same here. Now there are 2 pi bonds, so 1 p orbital needs to be, and this actually should be drawn straight out. This nitrile group should be drawn straight out. But we can have a p orbital coming out at you that's overlapping with this p orbital to make one of those pi bonds, which can overlap with the p orbital here, which can overlap with the p orbital here, and that should again be drawn as, that's a correction, because this is of course sp hybridized, so this would be rod-like. But we can have 1 p orbital that's not overlapping, or sorry, p orbitals, 2 of them here. One overlaps with the p orbital coming out at your eye. The other one would be normal to that, it would be 90 degrees oriented. So we could have one, again, that I'm putting in sort of shaded dark here, coming straight out towards you, could overlap with this carbon, which could overlap with this carbon, giving us a conjugated system. Of course, this one would also be conjugated. So important, conjugated systems are determined to be such only by looking at the location and number of atomic p orbitals. That's really the key, not alternating double and single bonds, not the number of electrons. It's really just the amount of p orbital overlap. That's important. 3 or more, and we have a conjugated system. So this would be a non-conjugated system, just an alkene, reacting with, and just what we've already seen in the past, HBr, a strong acid, give up a proton. This attacks a proton. We use Markovnikov rule, no stereoselectivity in the reaction, so we could put the proton on the carbon with the most hydrogens so that the positive charge is most stable by Markovnikov rule. Apply that. We get an intermediate. This next attack could come in from the front or the back if we consider the p orbital that's empty, but it doesn't matter. So we get just one product. Even though there's no stereoselectivity, there's only one product because this is not going to be a chirality center. But we have a little bit of a twist when we look at electrophilic addition, not to alkenes, but to a conjugated diene. It's a little different. Still a strong acid, still have to give up a proton. The question just becomes, where do we place it? Get away from this idea of Markovnikov rule. We've got to go with what is going to give me a resonance stabilized carbocation. That is most important. So please, as you take the jump from alkenes to conjugated dienes, leave behind any concern for Markovnikov rule, at least at the beginning. The first thing I must do is consider resonance stabilized carbocations. So I could attack with these pi electrons, and by resonance, let's again not consider Markovnikov rule. By resonance, I better put the positive charge here at the allylic position to what would be the remaining alkene. And since this is there's symmetry here, there is no A and B. These two pi electrons, we can just kind of tag them as both A, because if you closed your eyes, I could flip this structure over, and this one lands over here, and this one lands over here, and you would not be able to determine whether I had just left it alone or I had actually moved it. So this is a symmetrical dyne, Just pick one. Whatever's true for one is true for the other. But when I again attack, do not consider first Markovnikov rule. Just consider the positive charge has to go here if I'm going to use these pi electrons so that it's next to the double bond, as we have here. This would be allylic carbocation. This would be our allylic, and where we have three overlapping p orbitals, we have conjugation, not only in the dyne, but in the carbocation left behind, three atomic p orbitals with two electrons between those three atomic p orbitals. And then we could finish off. Once we make it to this allylic carbocation, we can have bromide attack either here, but since it's allylic carbocation, we know the positive charge can also be expressed here. So now we start to look at two products always that can be considered, at least two possible products from conjugated dynes reacting with strong acids. Two possible products. All right, let's get to those two possible products, because we have the allylic carbocation. By resonance, we know we have to go to the allylic position. We have two resonance forms with any allylic radical, cation, anion, any allylic cation. We have two positions. This would be a secondary carbon. This would be a primary carbon that's holding the positive charge. So right there we can see this would be, as far as resonance forms, a little more expressed than this one, because this has a secondary carbon expressing the positive charge in this resonance form, and this resonance form has a primary carbon. So we might have a little more contribution of this resonance form, a little more expression of the positive charge here. So we might expect this to be giving us always the favored product. Well, there will be some cases where this is favored, but there's also going to be a case where this one is attacked, or this one as a site for attack is favored. Where the nucleophile goes will sometimes favor this position, and sometimes it'll favor this position. We just need to know when this is favored and when this is favored. So we'll look at that. Before we do that, though, I just want to make sure the view of these cations, we can change the pictures we use to draw these allylic cations. Again, we can go to orbital theory. We can say we have the carbon-carbon pi bond with two electrons, and we have an empty p orbital next door, which has on that carbon a methyl group. So that's the picture, the orbital picture you want to go to when you see letters and lines is, hey, really what I have are two electrons, and when I move those two electrons over, the carbon on the end would have an empty p orbital. Now again, we said this is a greater contributor, so that's kind of reflected in what's called electrostatic potential maps. This picture is generated using computer modeling. It does show this carbon that's interior to be expressing more of that empty p orbital state where it's really between two, and this has just a little bit of blue. Blue is always a lack of electron density. Red is always an excess, so we're kind of in between with the green. Not a lot of electron density, but a little bit more than what's on this carbon. So you think, well, what is this really representing? Again, this is representing, kind of from a tilted view, the allylic carbocation, and this positive charge is most expressed here, but also expressed to some degree here by resonance. Let's talk about those two products we can form. When do we go to the secondary carbon, and when do we go to that end primary carbon? We go to this end primary carbon when we have thermodynamic control. Thermodynamic control. Meaning we're considering just the end. The thermodynamic controls of a reaction, any reaction, you're just considering the beginning to the end? What is the difference in energy of the beginning to the end? How can I get to the lowest energy end? The lowest energy end is to have this double bond such that it has 2 carbons off of it when we end. So we get to our final product. This carbon's bound to the bromine. The bromide comes in and attacks here. From this allylic carbocation, the bromide comes in not attacking here, but it attacks here because there's positive charge that can be expressed here by resonance. The pi bond moves over to this gap in the middle. So just to draw the picture of this, I'm going to sort of stay with skeletal over here. We can say that bromine attacks right here. The double bond then is connected to 2 carbons. It's a disubstituted alkene. If we look at the 1,2 adduct where we attacked the positive charge where it was favored, the nucleophile doesn't come in and attack the carbon here that was primary. But if it comes in and attacks that secondary carbon, and you say, well, which one is it attacking? Well, these are resonance forms, so it's really attacking both. We're just getting more of one over the other. If the positive charge here is attacked, then the double bond is on an end. It's only mono-substituted. So this is going to give us a little bit higher energy final product. It's a little bit higher in energy, so it's not as favored. Because we look at thermodynamics, we just look at beginning to end. What's the lowest energy point? If I were to allow enough energy in so it can go over all energies of activations, where does it settle? Well, it settles on the red product here, the 1,4 adduct, called that because the proton we originally added is way over at this carbon, and the bromine we added is way over at this carbon. They're 1, 2, 3, 4 in position relative to each other. But if we add the proton here and then have the bromide come in here, this would be a 1, 2 adduct. This is favored kinetically. The energy of activation is lower because more of the positive charge is expressed here, but it doesn't give us the lowest energy product. So we can favor this kinetically. This is the kinetically favored product, meaning at lower temperatures and fast times. Thermo is higher temperatures and long times. Kinetically favored is at lower temperatures and shorter time. Forms more quickly, forms favorably. So delta G of a reaction is key beginning to end. With thermodynamic control, activation energy is key. This typically favors the 1,2 product or 1,2 addition. Thermodynamic control, you have to look at your possible products to see which one is thermodynamically favored. Let's consider that, and let's finish with this example problem, putting it all together. So we certainly have 2 pi bonds that are different from each other, an A and a B, because it's not symmetrical. We can consider using pi electrons A to attack the acid in HBr, a strong acid, and put the, again, positive charge has to go here, so the proton would go here. That would give us this intermediate, and we would have a 2-2 combination if we consider the placement of where the positive charge can go. It can be here, and it can be here. If we use, this is using pi electrons if A. If we use pi electrons B, if B, then again we still have to put the positive charge here. Why? Because of resonance stabilization. It's very important to put it next to the pi bond. So we do that. This would be a 2-1 combination. Well, this carbocation is more stable, so if we have to consider 2 possible carbocations, go with the one that by resonance and inductive effect, considering the number of groups off of these 2 carbons that are expressing the positive, it's just a primary secondary. Here it's a secondary and a secondary. So we have to make the right selection of the carbocation. This is our winner because by resonance and inductive effect, it's most stable. So if we have choices, you have to pick the right carbocation. But once we have this picked, we know that the product, kind of remembering where the proton went here, the proton if A went here, so I'm just going to put this as far as 1,2 adduct. If we attack this position, that would be the 1,2 adduct. If we attack this position, it would be the 1,4. Let's go ahead and make those products. So we have the bromide coming in, attaching here. That would be our 1,2 adduct. This is again typically the kinetically favored product. There's some other things that go into why the 1,2 is typically considered the kinetically favored product. Proximity effect, you can look that up if you want, typically causes this to be the favored product kinetically favored, faster forming the 1,2 adduct. And we could also take this pi bond, and we know we can attack this position with the bromide. So that'd be the 1, 2, 3, 4 adduct. This is the 1, 2. And we don't know if this is the thermodynamically favored, or if this is the thermodynamically favored, or if there is any favoring. So let's look at this. It's a, if we circle the double bond, it's a di-substituted double bond, but so also is this. If we look at these two structures long enough, we'll start to notice, hey, in this particular case, even though we can attack the position here to get the 1,2 adduct, and we can attack the position here to get the 1,4 adduct, I think you'll start to notice that in this particular case, these two are actually equivalent. So for this particular diene, yes, we can consider the 1,4 and 1,2 as far as where we attacked, but they give us the same product. So are there two products? No, there's just one product. The 1,2 adduct and the 1,4 adduct give us the same final product. Do we have kinetic or thermodynamic control? Of course, no. We only have one product. Please, as you try other problems on your own, remember the 1,2 adduct is always the KF. And how do we find the TF? Well, the TF it's either one of three things. It can be on the same 1,2 adduct because the double bond that's formed has more substituents around it, or this can be the TF because the double bond formed has more substituents around it, or if they're equal, there is no TF. So this is the KF and the TF can be this same one, this one, or these two are equivalent in their final energies according to Zaytev's rule, number of substituents off a double bond. Well, that's a lot to chew on. We'll see in the next video where we consider Diels-Alder reactions.